Okay, we're back from the break, but something happened during the actual session where I forgot to hit resume on the record. So I'm going to re-record these first few slides and merge it into the overall presentation. So where we left off was we wanted to talk about the Hadoop resource management. And so there's this thing called YARN, which stands for Yet Another Resource Scheduler. And so basically, where Hadoop started was with Map Reduce as the primary workload, but we wanted to make Hadoop able to support multiple kinds of processing frameworks, not just MapReduce. And so there's a couple of examples here. For example, the resource management you can see as a layer that sits on top of HDFS. And so when jobs want to run on the cluster, they are actually going to work with Yarn first to get time on the cluster, to get resources in the cluster. I'm going to show you how this works. Here's a picture of two clients, and they're both trying to do some work on the cluster. Now, without a resource manager, you could imagine lots of different users possibly coming in, and they're just bumping heads, or they're over-consuming resource on the system. So just like how an operating system on a single machine is responsible for balancing multiple processes running concurrently, memory management, disk I/O queuing, that kind of stuff, we need something at the cluster level to make sure that we don't overutilize the cluster, to do scheduling and resource management. So here on client one, for example, will come into the cluster and says, I want to do some work. It will then go to the resource manager and say, I want to allocate some memory and CPU to do this work. The resource manager will then determine where to best run this work by looking at the utilization of the clusters and allocate, what's called this application master. The application master is, you can see it as a quarterback for the whole job, and it's responsible for then allocating additional containers as needed to get the job done through talking with the resource manager. And if parts of the job fail, the application master is also responsible for restarting it maybe on a different node. And so when the job is done, these containers are freed up. The application master returns those resources to the resource manager, and now those containers are available for some other job to run. Client 2 will come in, and maybe job 1 is still, client 1 is still running. Client 2 doesn't need to have any awareness of client 1. And client 2 is going to come in and talk to the resource manager. If the cluster is busy, the resource manager will just queue them up, right? So that we don't over consume. Again, you'll have the application master 2, which is doing work on behalf of client 1. It will allocate additional containers as required. The containers will contain a combination of memory and CPU. When it's done, returns those to the resource manager, and now those resources are available once again to other clients. So you can imagine what would happen if lots of users came on and they have different priorities. Well, that's where the scheduler comes in. The scheduler, you can set up different queues, like different priorities. And maybe you want to reserve 80% of your resources, for example, for general work. And maybe you got 20%, which is for high priority work, stuff that needs to always get done. So you could do this thing called capacity scheduling, where you could say, 20% save for high priority job and 80% for everyone else. And when that high priority job comes in, we're going to use that high priority queue. It's going to get time quicker on the cluster. So we can have some degree of prioritization. Now, when we talk about Hadoop and HDFS, I think I talked about some of the limitations of HDFS. It's a Java-based file system that sits on top of another kind of real file system, which is ext4. But that Java-based file system that is HDFS allows us to work with a file system that's virtualized, that's spanning multiple nodes. And that's a huge amount of value, right? Reduces the complexity. But with that file system, HDFS, it is an append-only file system. So it's difficult to do things that we typically take for granted, like a random seek. I want to go to a specific line in a file very effectively. So, indexing is kind of a challenge to do, an indexed file. If I wanted to update to a particular value within a file, that's also not an efficient process. There are ways to do it. They're kind of beyond the scope of this chat, but this stuff is always evolving. But generally speaking, HDFS is primarily an append-only file system. With HBase, this is another project that is commonly found in a Hadoop platform. So HBase is designed a little bit differently. They have their own file format, and also this write-ahead log technology, which is an in-memory kind of transaction log. And this combination of a file that's built for transactions as well as write ahead log capability that's in memory, that's replicated for consistency, allows us to do a transactional type workload on Hadoop. And in fact, it's really scalable. It's considered a NoSQL store. It's really fast. And basically, the way you work with it is get and put. So if I want to write a value, I would do a put operation and make sure I have a key. And if I want to get it back, I would use that key to get that value back. So if you think about mobile devices, for example, a lot of times NoSQL stores are great for mobile computing. A lot of times these are personal devices where I have a specific account on an app on a specific device. So everything I want to write related to that device is key-based lookups and key-based writes. And so HBase is a project you should be aware of. If you're looking for transactional key-based insert, update, deletes on Hadoop, you can look at HBase. Now, I mentioned before that if you like Java and you're good at Java programming, that's great, but you may not need to dive to that level every time you want to work with Hadoop. In particular, if I want to focus on analytics, I want to spend as little time as possible writing code and more time on analytics. So two key projects in Hadoop you should be aware of are Pig and Hive. Now, Pig is this language, and I'll show you some examples coming up, is this ability to write in a high-level language to do analytics. Again, I'll show you an example. So let me move to Hive. Hive is a favorite project on Hadoop. It's the first SQL engine for Hadoop, so there's a lot of love for it. Now, you should know that there's 23 or more SQL engines for Hadoop nowadays, both proprietary and open source, and they're all faster than Hive, okay? And now, the reason for this is because Hive is based on Map Reduce, and Map Reduce has a latency associated with it. They have gotten better at making it faster, but other SQL engines have just more SQL capability and also just better performance. But because they were there first, there's a lot of love for it. There's a Hive metastore you should be aware of, which is where we capture the metadata. That's a lot of the center of the universe for a lot of these SQL engines. You submit SQL to Hive, and Hive will convert that to MapReduce for you. So both these tools allows you to do analytics using a SQL language or a high-level scripting language without ever having to dive into Java code, which makes our lives easier to get analytics out of Hadoop.
I know it's very hard for you in the back to see especially, but let me kind of just give you a gist of it. So I'm reading a file. The file is just bytes, a bunch of strings, right? And how am I going to analyze it? Well, often we want to apply a schema onto it. And by schema, I mean I want to kind of have this notion of columns and rows that allows us to work with the data. So what it says here is load some file, and I'm going to define a schema for it. And the first column is going to be this character array, like a string. Second column is going to be integer. And then I'm going to do a filter. I could put a condition here where age is greater than 18, age is less than 25. Well, how does it know what age is? Because in my schema, it's a second column in the file. So it knows how to filter on that. The third thing is I'm going to load another thing called pages.csv. I'm going to again apply a schema. The first field is going to be a string character array. Second field is a character array. Now I can do joins. Join data, I can join the first with the second. I can do group bys, summations, sort the data based on something, and it generates all this stuff down here, which is Java code. So the comparison is I could have written this in Java, MapReduce myself, but in about 12 lines of code, I got my analytic, right? And I avoided having to write all that Java code. Talk about ingestion. So I guess an interesting thing about, so the term is Sqoop. Sqoop comes from SQL, like databases. And so the term is a Sqoop data in, Sqoop data out of Hadoop. And so turns out, well, we can use MapReduce to actually do a parallel extraction of data from my database system. So long as that database system has a primary key, because I need to know how a unique key that I can say, maybe I have a data set with a table, and the first column is numbered 1 and increments by 1 to a gazillion, right? Well, if I were to extract the data serially, I would extract row 1, then 2, then 3, then 4. It would take a long time. And I would probably, pin one CPU really hard on that source system. But what if I could identify that that key is unique, and I could say, I want to create a MapReduce job where each of the nodes establish their own connection. And between 1 and gazillion, I'm going to divide the key into 4 equal parts. And the first node is going to read the first 25% of the keys. The second node is going to read the second 25%. The third will read the third 25%. And the fourth will read the fourth 25%. And so that's the map phase. We're going to create a program that does that. There'll be a map phase. The map phase will then, each of those nodes will make their own connection. And now we're reading from the source system in parallel, right? 4 times as fast. And landing the data into HDFS. The reverse can be true. So in the reduce step, there's like nothing to do, right? It's just mapping and then pull the data over. Reduce, no op. On the export side as well, we can push data, right, into my target system as well. So each of these, in the map phase, I map the program. Each program establishes its own connection to the database and reads the data and pushes it into the database. So now it's ingesting into the target system. And so all this is a very simple command. You see Sqoop export, Sqoop import, provide the database connection information and the file that you want to get in or get out. And you're kind of off to races. No Java programming, right? So that's a very common tool that's being used nowadays. Yeah, question?
You provide an example for our DNS, but what level of NoSQL is there compared to the difference in performance-wise in the say MongoDB versus NoSQL platform?
Yeah, I'm not going to get into that. Well, let me tell you. It's really not fair to compare NoSQL systems to database systems. I'll tell you why. Because it's so dependent on the workload and the data set. So let me give you an example, right? If I have an XML payload that I want to store in a NoSQL system, or I can store it in a relational database system, and the relational database system takes that XML document and breaks it up into, because it's nested, right? It's hierarchical storage. They'll take the XML document, maybe store it across 3 or 4 different tables. To get that document back, I have to join the tables maybe to bring it back. Whereas in the NoSQL system, I have a key, I go get it, I get the whole document, right? So it can be faster in that use case. I think that where NoSQL systems are not as good as relational database systems is that like traditional SQL analytics, where I have to do like large scans. So the HBase example I gave you, for example, where I could do puts and gets really, really fast. If I want to do a summation on a specific column that's embedded in my NoSQL document or field, it's going to be doing it in a series of get, right? And each of those is costly. Whereas if I am reading it from a relational database system, I can read large blocks from a column store and block fetch and pre-fetch into a buffer pool where the data is there in memory before I even need it. And so I can actually perform that kind of analytic much faster in a traditional data store. So I think it's not, there's a lot of excitement about NoSQL stores for the last couple of years. And I think that what's exciting about NoSQL stores is that they are able to solve problems that are difficult to solve with traditional relational databases. Don't deny that. However, is it the solution to every problem? No, which is why I don't want to get into a discussion, because it's all philosophical. And it is really about understanding which systems are good at what, right? Like, when you deal with things like eventual consistency, right? Some of these NoSQL systems. Is that okay for banking? Would you be okay with your bank account if it was eventually consistent? Maybe not, right? But for something else, maybe, right? So what we have is, in this newer world, more tools available to us. And they're all good for the right purpose. Yeah? Did I answer your question? I don't know if I did.
I think kind of like depending on the volume of data, that's where probably SQL excel better than most.
But if the structure or non-structured data, actually I think more. But
Yeah.
If the non-structured, I can tell with the NoSQL much better.
Yeah.
But if the structured data, when you join with the key, will much faster. Let's say they already had a better algorithm behind the running.
Yeah.
So it's really depend on your data structure actually.
Yeah, I would advise anyone who's entering the workforce to not get too hung up on NoSQL is the answer to everything. It's not wise, I would say. I think they're very exciting. They solve a lot of problems we couldn't solve before. And there's some very specific use cases that NoSQL is perfect for. There's some where it's not. There's some problems that are really well served by relational, either on the ingest side or the consumption side. And it really, and there's so many choices, right? There's like hundreds of these things out there. It's really understanding your problem really well, what the use cases are, and then picking the right engine for that purpose. Yeah.
Is that the only tool for data ingestion, just Sqoop? Or?
No, this is just, there's like 20 things we could go into. I mean, you can go into Flume, you can go into Kafka, you can go into Storm, and Stream. There's a gazillion. I did a workshop for a customer. We narrowed it down to 12 options. And here's 12 things you could do to bring data in, and here's why you would use each different one. And that's the problem with Hadoop, is that there's so many, there's so many ways to do everything, and each of them have like their niche, right? Just like the whole NoSQL discussion, there's even within NoSQL solutions, there's different sweet spots. So, there's the great news is we got lots of choice. That's also the bad news, right?
Yeah.
So.
And is Yarn the only resource scheduler that's universal?
No. So good question. So Yarn is a very common resource scheduler, but there are, if you were to get a distribution, which means that some commercial vendor, be it IBM or there's a Cloudera and Hortonworks, they assemble a distribution for you. They're including Yarn. However, there's a lot of customers, I wouldn't say customers because they're not buying anything. They're just going to Apache.org and downloading it and rolling their own. They might use Mesos or something else, right? And again, it just comes down to understanding your workload, right? Don't want to get into what's better, Mesos or Yarn. It's really, they have their different sweet spots. And there's a reason why those users have chosen Mesos, because there's certain things that Mesos just does better than Yarn. But from...
So Hortonworks uses Yarn?
Yes. And does the IBM open platform, as does Cloudera, yeah.
Just to add in this comment, IBM also has the Ego, which is similar to Mesos and Yarn somehow.
So you guys, good point. So there's also Ego, and Ego stands for Enterprise Grid Orchestration. And actually, it's a really cool thing, but it's not open source, which is why most people have not heard of it. Is it changing?
Yeah,
I know they're working with Mesos, right?
actually, I work for IBM platform, so I'm working close to the Ego guys, and there's an effort to put some cool things on Ego running right now, very mature stuff on top of Mesos. So we are migrating functionality to Mesos.
So you're doing the Microsoft thing? Proprietary.
Yeah, question at the back. How it does deletes?
How it builds up something that was like destroyed data.
Oh, okay. My knowledge is fairly rudimentary. So what I recall is that if you have a block of data, and let's say that you perform some kind of update to something that belonged in the data, if you enabled the feature, so it's disabled by default, first of all, because it doesn't always work. That's what I heard. If you were then to make changes to the file, the changes, because remember the original data is immutable, right? So the changes are then appended at the bottom for those for the data that changed. It's kind of appended at the end.
So it is imprinted, and that's why if those files delete, it actually can build it.
Well, when you go to read that block, it has to read the delta as well to determine what's the latest version of that piece of data, right? So it's kind of, and you can imagine if you make lots of changes, the delta part starts to get really large. So there's actually this asynchronous grooming process that rebuilds that block as it gets large. And I pretty much told you everything I've learned on that, because I don't use that feature, so yeah. Okay, cool. So so just back on the Symphony. So IBM makes some really cool stuff. One is Symphony, and they have implementation of Map Reduce as well, which actually is a really efficient Map Reduce implementation. That it was really good if you have again sweet spots, right? If you have a lot of short kind of scheduled jobs, Symphony is really good for that. It also has some really cool things that enterprises care about, like chargeback ability. So if you want to build an ability to do resource chargeback to your company, You start with Symphony and you have this atom module that actually can do billing for you. So you have a departments, right? You can actually say, I'm billing you, Department X, for this amount of usage in the cluster, and I'm billing you this much. So customers like that, right? These are the features that, aside from technology, enterprises care about. There's stuff like resource reallocation that's dynamic that Symphony can do, which is really cool. So you have a job that's running. Remember I talked about the Yarn capacity scheduler that says, I'm going to use 80% for everyone else, but I'm going to save that 20% for really important people, right? Well, it turns out that Yarn is not really good at dynamically adjusting that. You kind of give up that 20% capacity because you want to have it available to others. There's a little bit of elasticity there, but it's not that elastic. Well, Symphony has kind of solved this, and they're actually able to dynamically allocate and deallocate. So typically for very strict SLAs, Symphony is a really, really good choice. So you can actually plug Symphony into your Hadoop, be it Hortonworks, I think it's Hortonworks, also IBM Open Platform. I think they're probably looking at other platforms. So again, this is the enterprise grade stuff that is not available in open source, but for customers that need it, it's really beneficial. I'll mention GPFS since you're here. I'm a huge fan of GPFS. So you think HDFS, GPFS, right? Remember that problem where you have a Java file system that sits on top of another file system, and you can't update the file and those other kind of things, and it doesn't like small files, right? And most people, that's going to be great. It's going to be just fine, right? There's a lot of people using Hadoop out there that's nothing wrong with that at all because their use cases are just fine. But let's say you did need updates. Or let's say you want to do transactional workloads on that file system. Or let's say you didn't want to make 3 copies. You want to use some kind of efficient erasure encoding, right? Maybe you want replication over large distances really efficiently. Well, GPFS can do that, right? And it speaks Hadoop. So GPFS today has a name node capability where it can actually, if an application talks to GPFS, GPS will go, oh, you're talking to me like a name node. I'm going to respond to you like a name node. And so it's called HDFS transparency. By the way, I will take credit for that feature. I actually went to IBM Almaden Research Center, and I told them they had to do that. So again, I am the product strategy guy, right? Okay, so Hadoop distributions. What is distribution? Well, Linux kernel is a very, very small piece of thing. A distribution like Red Hat combines all these neat utilities like gunzip and gzip and whatever else is utilities, right, that are in a Hadoop platform, different shells and things like that. So, and they package it so they can support you, right? So there is a notion of Apache Hadoop, which you can download and use yourself, but you could assemble those 20 components yourself. Or you can buy distribution. Of course, we're IBM today, so I'll plug the IBM Open Platform, which will just do it for you, right? You choose it being supported by IBM. There is an initiative you should be aware of, which is Open Data Platform Initiative, or ODPI now. And basically, with so many moving parts, it's really difficult to write an application that will run on Hortonworks and then IBM and then Cloudera, for example. It's really challenging. So what we're trying to do is, all the people got together and decided to form this consortium. It is run under the Linux Foundation. And basically, they're building kind of certification tests to build more consistency in the platform. The goal is that the distributions can align with these standards so that I write a program, I can run it across different distributions with more ease. Not perfect yet, but it's with more ease. And there's kind of 2 branches to this. One is operational, administrative. The other is runtime. So two kinds of compatibility. You can look that up, Open Data Platform.